By the time I came into my 9 a.m. meeting, there were a couple of people already saying, something has happened, we don't know what it is, there's been some sort of event. And so that was the point where I just sat in my office on my own looking at this, and I thought, wow, if this really is proven to be a real event that hasn't occurred for any strange reason, then this is so clear. It was amazing.
Welcome to a Face Project podcast.
Hello?
It's just pure life. It's pure
my
innocence.
mom
it's
is a
pure
writer. My
gratitude.
So I ended up in America.
I am an adopted
because
Korean and have been all my life.
It's a perfect blend of science and creativity.
I was screaming, I will live over here till I die.
Hi, everyone, and welcome to a Face Project podcast, episode number 3. I'm your host, Natalie Jennings. Today's story features one scientist's perspective on the recent groundbreaking scientific discovery of gravitational wave detection. And since this story covers topics like gravitational waves, Einstein's theory of relativity, and black holes, we thought we'd ask a few random people what they know about black holes. Here's what they had to say. What do you know about black holes?
Nothing. Stuff gets sucked into them. And I don't want to be near one. That's about it.
I know absolutely nothing about black holes. I'd love to know more about black holes. Call me.
Black holes are a metaphor for the human experience. And the human soul is a black hole for other human emotions. And there is no fate but to be destroyed in another person's black hole. Like if you get sucked in, you're dead. Not dead, but it's a metaphor, right? So
I'm asking you what you know about black holes.
I know that it's infinitely dense and infinitely massive, and it draws everything near to it into its gravitational pull, and that our only knowledge of it is what we can observe from, thousands of light years away.
Thousands and thousands, perhaps.
Is it thousands of thousands? I don't even know.
I know that if you go in one, you don't come out, and that's about it, I think. I don't know a lot about them.
Although I'm still wrapping my brain around space-time and general relativity and pretty much anything Einstein ever came up with, this story offers a unique perspective of Earth and space from one astrophysicist's point of view. And if you're interested in some supplemental reading and some visuals for what you're about to hear, visit our website and look under the podcast menu for Alastair's story. There you'll find links to a number of articles written about gravitational wave detection, as well as some photographs of Alastair himself.
When we actually detected the event, I think one of the things that surprised me was that although I knew the sort of things that might be generating gravitational waves, the full story about the event is actually really quite spectacular, because it occurred 1.3 billion light years away. That means that this event happened 1.3 billion years ago. So at the time that these black holes collided, on Earth, we were just starting to get multicellular organisms existing. So this predates the dinosaurs by a huge period of time. the way that life on Earth was at the time was, we were starting to get like clumps of algae growing in the oceans, and so the idea that now we've been able to to detect that 1.3 billion years later as this wave came through the universe is kind of amazing to me. When I was growing up, my dad was a scientist. He was a geologist, and so certainly being around him, it just seemed very natural doing research and doing things for myself. He was always building things, mending things around the house. He's a very, very practical person and would always do things himself. I can remember when I was a kid being on holiday with him, and rather than buying a kite, he would build one out of sticks that we found in the yard and sheets of plastic that were old trash bags, and and that kind of spirit of doing things for myself has really stuck. That's just how I am about things. I always try to mend my own cars and work on my own house and stuff. So growing up, that was certainly the environment that I grew up in. And then when I was at university, in one of my final years, I had to do a library project. And so I came across this gravitational wave project, and it turned out that not only was I interested in it at the time when I did this library project, but it turned out there was also a branch of the gravitational wave research that was being done in Glasgow at Glasgow University. So it seemed like a natural thing to apply for. It was a very exciting new kind of research that other people weren't doing. I like the idea of going to do research because it's something that you do it on your own. You kind of make your own way in it. You decide what projects you're interested in, and you learn the skills yourself that you need. So it's very much a kind of personal thing. It's not like a regular job where you might have something that you're trained for formally and then you go and do it. Physics is much more of a kind of exploration because you really have to do whatever it takes to get the experiment to work. So that means learning a lot of new skills and trying to be open to new things. And so it was very exciting, actually, finishing my undergraduate degree where it was all the regular kind of examinations and regular teaching, and then suddenly coming into this environment where you're really off experimenting on your own and doing your own stuff. And to be honest, everything I've done since then, being a PhD student and then being a postdoc in Glasgow and then at MIT and then Caltech and then being a laser engineer, it's all very, very similar work. It's all just the same thing, trying to figure out how to do things and then going and getting it done. I think being involved in scientific work does really change your viewpoint on life because, first of all, you're really driven by reason a lot of the time. So you're constantly kind of trying to think things out in a way, which can actually be a bit difficult to deal with, because a lot of time people don't just deal with reason, they deal with feelings or, I think it's quite common for scientists to come across as cold and not very friendly or argumentative. And that's, that kind of goes with the territory. It's hard to switch that off when you've been at work all day and, you come out of that environment. But then at the same time, you understand a lot more about the universe that you live in. You don't just look at the night sky and see stars. You look at the night sky and you see the universe. And that's quite exciting. You look at the sun and you understand the fusion processes that make the sun. That at the center of the sun is producing iron. All of the metals that we have here on Earth came out of the center of stars. That kind of changes your perspective on things. When you pick something up and it's made out of a heavy metal like gold or platinum or something, that came from the center of a neutron star, not just a regular star, but one of these dead stars when it exploded, spat out these heavy elements we have on Earth. And I think a lot of people go through their daily life not realizing that we are made of stars and the things that we come across every day were created in these extraordinary events in the universe. So it definitely gives you a different perspective on things. In our universe, 5% of it is matter that we actually know what it is. You know, things like what we have here on Earth or stars, gas, rocks, these sort of things. That only accounts for 5% of the universe. 95% of it is made up of these two things called dark matter and dark energy. And we don't know what those are. All of the other types of astronomy that we have at the moment involve light. X-rays and microwaves and ultraviolet, these are all just different parts of the light spectrum. We can't see them, but they're still on a spectrum. It's all still electromagnetic waves that are coming in, the same thing as light. This is the first time that we have done astronomy that doesn't use light at all. We are directly measuring the gravitational effect from this distant source. And that's very exciting because there are a lot of things that can stop light waves getting to us, including the gravitational pull of a black hole. So black holes don't emit electromagnetic radiation that we can detect. They just look black. And so the only evidence that we have of their existence is based on either the effect that the black hole has on nearby stars. We look at the motion of stars and can calculate that there's a black hole there. Or we might see gravitational lensing, and that's basically the gravitational pull of the black hole being so strong that a star that is behind it has its light warped as it goes past the black hole. And from our side, it might look like a ring of light. So instead of a star looking like a single point, it now looks like a ring because the black hole has bent the light as it passed. We don't understand properly what is inside a black hole because the laws of quantum mechanics don't work inside black holes. And so everything that we understand about matter that we see here on Earth is not true inside a black hole. A black hole has gravity that's so strong that light can't escape from it. And so any light that came off the surface of it gets bent back and sucked back into the black hole again. Literally nothing escapes from the black hole. So LIGO stands for Laser Interferometric Gravitational Wave Observatory. And the first part of that is laser interferometer. That's what type of instrument it is. Obviously, the gravitational wave observatory part should be self-explanatory. You know, once we detect gravitational waves, we then become like an observatory that tries to do astrophysics to figure out what's behind the gravitational waves we've seen. So LIGO itself is an L-shaped each arm of the L is about 2.5 miles long, and when the gravitational wave comes through the detector, one arm gets compressed and the other one gets stretched. And it's that relative change in length that we're incredibly sensitive to. In fact, a gravitational wave coming through the detector changes the length of the arms by roughly 1/1000th of the diameter of a proton, or 1/1000th of the diameter of a hydrogen atom. So it's an unbelievably tiny effect. So we have a massive team of people that are working on that. And it really is an incredible thing to see when you go to the site, just how beautifully built everything is, how all of the electronics are, made by professionals, and all the computers are maintained by professionals, and all this custom software that they all run. Part of my job is taking the research that was done on certain parts of the interferometer and helping to do the engineering to install that at the sites. I think my favorite part of my job is really the times that I get to use what I think are my personal skills, which is kind of building things and putting things together, and the parts of it that are a bit more like an art or a craft. So one of the jobs that I did for Advanced LIGO was to produce the very, very thin glass fibers that are used to hold the mirrors in place. And so I was one of a group of people that designed and built the machine that produced these fibers. And actually going out to the site and running that machine is really kind of good fun because it feels like something that I've been involved in since the beginning and something that I've built. And, you know, there is a sort of art to producing them. It's not just completely just science. And so that's kind of enjoyable going and doing that. Really, the day of the announcement was extraordinary because to see the press's reaction and to see, I was sitting at Caltech at the press conference at Caltech and watching the press conference that was being held in Washington, D.C. And the moment that the detector of LIGO said, "We've done it, we've detected gravitational waves," immediately all of the headlines on all of the online papers started changing, you know, and you could go to the BBC and it's front page of the BBC, front page of the Guardian, and that was just completely mind-blowing to me. To see that reaction was just extraordinary.
Ladies and gentlemen, we have detected gravitational waves. We did it.
The actual event itself was caused by two black holes. This is the first time that we've directly been able to see black holes. One of the black holes was about 36 times the size of our sun, and the other one is about 29 times the size of our sun. So these are really, really heavy objects, but their physical size is much, much smaller. They're about the size of the state of California, so they're unbelievably dense, very, very compact objects. Over time, they've been sucking in more and more mass to get to the size that they are. And eventually, as they were coming towards each other in space, they got locked into each other's gravitational pull. And that caused this sort of spiraling where they started orbiting each other and gradually getting closer and closer and closer to each other. And the part that LIGO is able to see, because of course this has been going on for a very, very long time as they got closer together, the part that LIGO saw was the last 0.2 seconds of their existence. By the time that they actually collided with each other, they were circling each other 75 times a second. So if you can imagine something that's two objects that are about 30 times heavier than our sun, cycling around each other 75 times a second before finally colliding into each other. At the point where they finally hit each other, they were moving at roughly half the speed of light. So it's a pretty extreme event. And the gravitational waves that come out of that, there was so much energy in them that the final black hole that was created was actually 3 solar masses lighter than the two black holes that started out. So it lost the equivalent amount of energy of 3 times the mass of our sun, just by E equals mc squared. You know, energy is the equivalent to mass. So when these things collided, they lost 3 times the mass of our sun in energy, which is just a colossal amount. And at the point where it was emitting the largest amount of gravitational waves, the energy output from this event was 50 times brighter than all of the stars in our entire universe put together. So it was an absolutely huge event when it happened. I think it took about a day or maybe 2 days for one of my colleagues at MIT to take the data and do some very, very simple processing on it that allowed us to look at what had happened. And that was the point where I knew it was real, because a lot of our data analysis is done in an exceptionally complicated way, which even for a scientist like myself is hard to understand. And so when you get the results back from a complex data analysis, for me, it's very difficult to fully appreciate what has happened. What my colleague at MIT had done was a very, very basic thing. He just put a couple of filters on it, very similar to kind of like audio filters you might have on your hi-fi. you can turn up the bass or the treble. Effectively what he'd done was turn down the treble and turn down the bass so that you were just seeing this kind of mid-frequency. And the moment that you did that in the data, you could see it. You could see the signal from the two sites looked identical. And it had all of the classic features of what we were already looking for these binary black holes. The soundbite you just heard is the sound of two black holes spiraling around each other and then getting closer and closer and closer and faster and faster. That's why you hear this increase in the frequency. And at the very, very last second, they collide, and that's where you hear this kind of pop right at the end. You can't really hear it by ear, but after that, there's also a little, very tiny second of ringing as this black hole that's being created kind of rings down and loses some energy. And those three individual sections, the part where it spirals and the frequency increases, the part where you hear the pop, and the part where you hear the ringing, they all tell us something about what happened. The part where the two black holes are spiraling around each other allows us to actually calculate what the mass of the black holes is, because we can work that out from the frequency of how fast they're going around each other. The part where you hear the pop, where they collide with each other, that actually allows us to work out the distance to this event. That's how we know that it happened 1.3 billion light years away, because we know from how big that pop was exactly how far away they are. And the final part where they ring down tells us a lot about the black hole that was formed. We can work out how large it was, and that's how we know that it's actually 3 solar masses less than the 2 black holes that began this whole thing. So Einstein was the first person to come up with this concept that space and time are linked, and that gravity is actually caused by space-time being warped by large bodies, large masses, actually deforming the fabric of space itself. So space and time are not two completely separate things. And that's a bit difficult to think about, because as humans in our daily lives, we experience them as being very separate. We move through 3-dimensional space, and time is this sort of linearly occurring thing. So to actually think that space and time are inextricably linked into this thing that Einstein called space-time is very different for humans to really conceptualize. The gravitational waves themselves were created from the black hole. They were created from mass that was previously a black hole and has now come past the Earth and warped our space-time on Earth. And we've been able to measure that. And the easiest way to think about it really is if you imagine a trampoline with a bowling ball sitting on it, and then if you think about rolling marbles past that bowling ball, the surface of the trampoline itself has been warped. And the marbles that you throw past, they're not being attracted in towards that bowling ball because of the gravitational pull of the bowling ball. They're moving around it because the actual surface of the trampoline itself has been warped. And so Einstein's view of gravity was essentially that large objects like stars, like our sun, were warping the space-time around them, and the planets that are in orbit near them are actually just moving through the space in the straightest line that they see. You can imagine that if you had 2 bowling balls and you kind of caused them to kind of roll around each other in the middle of a trampoline, you might get some little kind of ripples traveling out across the surface. And that's basically how Einstein envisaged gravitational waves. So it's like if you imagine standing at the edge of a pond and throwing a stone into the pond, you would create ripples. And they would move outwards like kind of concentric circles. But to somebody who's standing on the other side of the lake, they would just see these kind of straight lines kind of coming in towards them, they might wonder what it was that had caused these ripples that are coming in towards them. And that's really what it's like for us on Earth trying to detect gravitational waves, because we see these coming in and then we have to try to work out what caused them and where they occurred. This discovery is so significant for a number of reasons, really. The first one is that Einstein predicted gravitational waves, and in his lifetime, he never believed that we would be able to detect them. For us to be able to confirm another part of general relativity is really quite exciting.
It followed from the special theory of relativity that mass and energy are but different manifestations of the same thing, a somewhat unfamiliar conception for the average mind. Furthermore, the equation E is equal mc square, in which energy is put equal to mass multiplied with the square of the velocity of light, showed that very small amount of mass may be converted into a very large amount of energy, and vice versa. The mass and energy were in fact equivalent, according to the formula mentioned above. This was demonstrated by Cockcroft and Walton in 1932 experimentally.
When you see two black holes that are so massive, moving around each other so fast, the relativistic effects that you're seeing there are extremely strong, really, really strong, and it's like nothing we've ever seen before. The emission of gravitational waves from black holes was a theory that has now been proven, and also black holes themselves were only ever indirectly observed. This is the first time that we've seen a real signal from a black hole. I think one of the things that I constantly think about is how we are at a new frontier in science and technology. I mean, the world has never been like this before. If you go back 100 years, science was unbelievably crude. 100 years ago is the point where Einstein had just come up with general relativity. And so if you go any further back beyond that, you really are at a time when we didn't have computers. We were only just building the big telescopes that we have now to look at the universe. And so the way that science and technology has developed in the last 100 years has just completely changed our understanding of the universe. One of the reasons Einstein didn't believe we would detect gravitational waves is that in his lifetime, he didn't know about black holes. And the fact that now people that you talk to in the street understand that black holes exist, that's a real triumph for science, because it's not just people in ivory towers learning about this. The public are funding this research, and it's really important for the work that is done to be communicated effectively to the public. It's a responsibility for scientists to have. And so it's really exciting to me to see the media reaction when we had this recent detection, and to see media correspondents really going out of their way to try to describe this as carefully as they could and as accurately as they could. And that was really very exciting. I think it changed things in ways that I wasn't expecting. So first of all, I was really pleased for my parents, because they put me through university and they supported me the whole way through my education, and all the way through my PhD they supported me. I was just really pleased for them that I had something that had come out of it. I could say to them, if you look at the paper, you're going to see that we're in the paper, and that was really exciting. And to have friends of theirs phone them up and say that they'd seen me in the paper was really exciting as well. From a personal point of view, I've heard from a lot of people I hadn't been in touch with for a long time, and people I went to high school with, and that was really nice as well, to know that they've kind of seen that I'm doing this and that I was involved with it and wanted to congratulate me. So that was exciting. Yeah. This is really kind of closing the lid on all of the all of the general relativity predictions. I mean, it's such a funny thing. It's really surreal because you know it's like a completely once in a lifetime thing. Like, so you kind of realize like, wow, this is never going to happen again.
Thanks for tuning in, everybody. If you are looking for some more resources and maybe some visuals to back up that story, feel free to swing by our website, afaceproject.com, look under the podcast menu, and find Alastair's story. You'll find a bunch of things on his page that can maybe help add to what you just heard. This episode was recorded and produced by myself, Natalie Jennings, with help from Daniel Zamzow, web layout and design by Aaron Woods, photography by Jonathan Hansen. Most of the music samples you've heard today were from Eric Matias of soundimages.org. Additional audio clips were from the Public Archive. The gravitational wave clip you heard was from LIGO, and also the announcement clip from the BBC. Thanks for listening, and we will be back in a couple of weeks with our next story. If you would like to share your story, share your music, or if you're a photographer interested in sharing a photo essay with us for our magazine, please check our website for all of that information at afaceproject.com. We'll see you in a couple weeks.
To be here and that 0.2 of a second where we detected it was like, that was our one chance. That's gone now. You know, that'll never happen again. That's so strange.